Hello and welcome to our video about producing electric current. Since we now know what electromagnets are, we're going to talk about electromagnetic induction and generators. We're going to review a little bit about a direct and alternating current. We're going to look at what transformers are and how we can calculate the output voltage in transformers. So remember, we talked about electric current being able to create a magnetic field. When we have an electric current, a magnetic field is created around that current. And about a decade after the discovery where we learned this, two scientists working very independently of each other, Michael Faraday in Britain and Joseph Henry in the United States, they both discovered that moving a loop of wire through a magnetic field causes an electric current in the wire, which was an interesting idea. It's the opposite idea that we have going on here, electric current creating a magnetic field. Now we're looking at moving a loop of wire through a magnetic field and generating an electric current in that wire. This is what we call electromagnetic induction. It is generating electric current by a changing magnetic field. So if we look at our illustration of electromagnetic induction right here, we see that this wire loop, in this case it's actually a whole coil, a lot of wire loops, is moving relative to the magnet. We see from this picture to this picture, the wire coil is moving relative to that magnet, and because of that, the magnetic field inside of this coil, or inside it, even just a single loop if it were not an entire coil, the magnetic field inside of that coil is changing over time, and therefore electric current is induced or generated through that wire. So electromagnetic induction is very useful when we talk about generators. And most of the electrical energy that we use every day is provided by a generator or multiple generators. And a generator is simply a device that uses electromagnetic induction to transform mechanical energy into electrical energy. Here is an example of that, transforming mechanical energy into electrical energy. You've probably seen these flashlights that have a manual handle right here. And as the person supplies this mechanical energy by turning that handle around and around, that coil, which is inside of the flashlight here, inside the generator of this flashlight, it's being rotated by that mechanical, external mechanical energy source when you turn that handle. And that supplies the mechanical energy that is then converted into electrical energy by the generator inside of that flashlight. So when we look at that diagram of a generator, it should look very familiar to you because it looks a whole lot like the simple electric motor. Only we are putting mechanical energy into this system and creating or transforming that into the electrical energy that we're getting out. We can do this one of two ways. Either this coil, we can make this coil rotate right here. We can cause that to rotate mechanically, or we can rotate the permanent magnet around that. Power plants, large power plants usually operate by rotating the permanent magnet, and that's how they induce the current in the stationary coil. So how is electricity generated in your home? Well, in our home or in our school, the electrical energy that we use comes from a power plant. And that power plant has to have some energy source. And there are a variety of different energy sources. The power plant could be burning fossil fuels. It could be utilizing nuclear reactions to produce thermal energy. It could be using wind or falling water. All of these are just different ways that power plants will be provided with their energy source. That energy source, whatever it is used to turn a turbine. In this case, here's an example of turbines up there, wind turbines. And a turbine is simply a large wheel that's rotated when it's pushed. could be pushed by water, by wind, by steam, by a lot of different things. And here's just an example of some being pushed by wind. That turbine then would be connected to a rotating magnet inside of a generator. Here's an example of a very, very large electromagnet, which is kind of exciting to see. Here's the man standing there, how much smaller he is than this great big electromagnet. That rotating magnet induces current in the coil. It's just on a very large scale, much bigger than our little hand generator flashlight. So let's just review what we've discussed so far to get this straight in our minds. Motors. The electrical motor converts electrical energy into mechanical energy, whereas generators can take mechanical energy and they convert that into electrical energy. So that's the difference between motors and generators. Also, just a quick review about direct current and alternating current. Remember, direct current, DC, is the electric current that always travels one direction through a wire, whereas alternating current, or AC, is electric current that reverses the direction in a regular pattern. That being said, let's take a look at transformers. What are they and how do they make use of electromagnets? And we are not talking about this kind of transformer. We're talking about a different kind of transformer. Devices that either increase or decrease the voltage of an alternating current, AC. So we can have either step-up transformers or step-down transformers. A step-up transformer would take the alternating current that's coming in, and it would increase the voltage of that current so that the alternating current going out of that step-up transformer would be greater voltage than what was coming in. This example would probably be an example of a step-down transformer. It decreases the voltage. So we're starting with a higher voltage, and then going out, there is a lower voltage leaving the transformer. So how does this work? Basically, we have the alternating current coming in through a primary coil. A transformer has two coils, primary and secondary. Here's the primary coil and the secondary coil. When the alternating current comes into the primary coil, that primary coil's magnetic field magnetizes this iron core that it's wrapped around. The primary coil's magnetic field changes direction at the same rate as the current in the primary coil, and the magnetic field in the iron core also changes direction at that same rate, sometimes referred to as frequency, the rate that it's changing. The changing magnetic field in this iron core induces alternating current in the secondary coil. And so we end up with our input current and our output current alternating at the same frequency. We can calculate the output voltage of a transformer using this equation. Actually, this equation is a better one to use, but these words describe what this equation is all about. We have our output voltage, measured in volts, obviously, divided by our input voltage, measured in volts. That's equal to the number of turns in our secondary coil divided by the number of turns in the primary coil. Here's just another picture, a little schematic of a transformer. Now let's try doing a problem with this and see if we can plug values into this formula and calculate input or output voltage for our transformer. So in our example, we have a transformer that has 150 turns in its primary coil and 50 turns in its secondary coil. We also are given the input voltage as being 12 volts. What is the output voltage? So let's write down our formula and look at what we know and see what we can substitute into our formula. Here's our formula. The voltage out divided by the voltage in equals the number of turns on the second coil divided by the number of turns on the first coil. And we are given the input voltage is 12 volts. I'm going to write that here, 12 volts for the input voltage. I also know that we have 150 turns in the primary coil. So that's 150 turns in the primary coil. And we have 50 turns in the secondary coil. So that would go on top. 50 turns in the secondary coil. And the question is, what is the output voltage? That's my variable. That's what I don't know. So I can do this problem a number of ways. I can cross multiply, or I think what would be easier in this case is simply multiply both sides by 12 volts, because then my 12 volts cancel on this side. And I am simply left with the output voltage equal to 50 divided by 150, and then that whole thing is multiplied by 12 volts. So my output voltage is 4 volts, and that makes sense. This is a going from 12 volts to 4 volts. It's a step down transformer, and there's my answer. So one more item to address before we leave this whole idea of transformers, and that is the use of transformers in transmitting electrical energy from the power plant to our homes. Once the power plant is ready to transmit all of that electrical energy to homes and businesses, a lot of the energy, the electrical energy, is converted into thermal energy because of just the resistance of the wires. These wires carry the electrical energy over very, very long distances. It can be many kilometers, and the electric resistance increases as the wires get longer and longer. And so large amounts of that electrical energy is transformed into thermal energy, which heats the universe. And it's not really what we want to be doing with that. So power companies use a step-up transformer to increase the voltage prior to transmission of that electrical energy. The voltage is increased to over 100,000 volts, actually. Then that electrical energy is transmitted along the power lines, and afterwards there is a step-down transformer which decreases that voltage to 120 volts, where then it is ready for consumer use in homes and schools and businesses. And that is the process shown in that little diagram there. Quick review: know what electromagnetic induction is, what generators are, how they're used, how they operate, difference between direct and alternating current, what transformers are and how they work, and how to calculate the output voltage of transformers. Here are a few advanced ideas. Have fun with those, and I look forward to seeing you in class.